So Newton's laws of motion. So in the 1600s, roughly around the same time that Newton also invented or formulated the theory of calculus, Sir Isaac Newton proposed three physical principles, okay, that govern or control the physical behavior of an object. So basically, what he discovered is the way that the motion, or just the description of unit one, kinematics, is related to the what? To how the forces externally, again, externally, not internally, are acting on some object. Okay, these are called Newton's laws of motion. Okay, the actual official name for them is laws of motion, not principles of motion, not rules of motion, not suggestions of motion. These are laws of motion. Okay, all physics is eventually more complex applications of these three very basic laws. Sorry, yeah, very basic principles. Just so you know, everyone, just so you know, they work for absolutely any object or any system as long as the system has definitely two distinct features. Number one, okay, let me say it from another perspective. These laws fail, but only in two cases. Case number one, if things get very what? Very, very small. How small? Like what scale do you think? Atoms, yes, atomic scale. For then, Newton's laws actually don't work. They invented what? Does anyone know what was the type of mechanics that they invented? You sometimes hear that word in chemistry. You know, the mechanics that applies to hydrogen and to atoms and to nucleus and so on. Quantum mechanics, thank you. Quantum mechanics was invented basically to replace Newton's laws of motion for the very small. So if the size is atomic scale or microscopic, these fail, and you have to understand quantum mechanics. That's the first case that they fail. The second case is if the particles go very what? Very fast. Then it's not quantum mechanics that you need. It's what? What's the theory that Einstein proposed that actually governed the speed of light? Re- Relativity, exactly. So Newton's laws fail in two cases, for the very small and the very what? Fast. Well, every single thing you're going to apply in this course, and even as a first-year physics student, and if you eventually become an engineer, will always be what? Will always be big and slow. Okay, think about it this way. Big and slow, Newton's laws of motion. Done. That's it. Nothing fails. Okay, so let's start talking about the very first law. So Newton's first law. Okay, so I'm just going to introduce it as a scientific principle, and then we'll talk about what it means. Okay, so what is the statement of Newton's first law? The statement, the official official physical statement of Newton's first law. It says, if the net force, see, that's why you had to learn the net force first. Okay, if the net force on an object, by the way, when you say on an object, you mean by calculating them externally. On it means from the outside. So if the net force on an object is what? Zero. Exact, perfect zero. Not an approximation. Exactly zero. The object maintains or is in a state of either. No other choice. If the net force on object is zero, the object is either in one of two states. It's either at rest, which means stays stationary or not moving. That's the first possibility. The second possibility is moving at constant speed in the same or in a constant direction. Any object with a net force of zero on it is either going to be staying at rest or cruise controlling along the same direction. Always. There's no other choice for what the object state could be if the net force on it is a perfect zero. Okay. In other words, if you combine, if the combination of all external forces on an object is a perfect zero, if the combination of all forces externally on an object is a perfect zero, bless you, which means all forces did what? Canceled each other out, the object is either at rest or in uniform motion. Remember, we did two kinds of motion in unit one. One of them was uniform motion, which is this, just going straight, maintaining my direction and maintaining my speed. Does anyone remember the name of the other motion? Yes, uniform acceleration, which means I'm still going straight, not changing my direction, but what's happening to my speed? Speeding up or slowing down. Well, guess what? We do not actually have uniform acceleration or deceleration for Newton's first law. we have it for, we have only uniform motion. Okay? So, okay, so for example, right now, all of you, are you moving? So that means on all of you right now, the net force on you is what? Is 0, which means all the forces on, so okay, for example, can you tell me the forces on you right now? Just list all the forces acting on you right now. If I sketch an FBD of you, what forces do I have to put on it? Gravity points down. But you're not falling down, so there must be a what? A support force up. What do you call that? Normal force. So now you have what? You have gravity and normal. Do you have any other applied forces on you? Is someone pushing you? Is someone pulling you? Are you connected to a string or a spring or a cable? So there's no tension. Are you under any friction? No, because you're not. So that means what? Those two forces on you must have a net force of what? Of 0, because you are not moving. Okay? Vice versa is tricky, everyone. If you say, oh, there's an object outside with a net force of 0, can you describe its motion? I don't know, because it could be in how many states? Sorry, in one of how many states? 2. If I told you, for example, there's an object outside with a net force of 0 on it, you could tell me it's either what? At rest or constant speed, cruise controlling in the same direction. See, to go from here to here, you have two possibilities. But if you know one of these two cases, you at least know for sure that the net force is 0. Okay? All right. Again, most of today will not make 100% much sense unless we what do the problems we're going to do tomorrow. Okay? Okay. How many people have heard of the word inertia before? Inertia. Okay. Ammar, what's, again, in as simple as you can put it, okay? No need to fancy it up. What's your understanding of inertia? Sorry, say that again. If you're what? Okay, so if you're driving and slam the brakes. Okay. So where's the inertia in there? Uh-huh. Exactly. Perfect. Everyone, inertia is a property of all objects in the universe that has one feature to it, mass. Any object in the universe that has mass has what? Has inertia. Okay. What is inertia? Inertia is the what? The object's ability to fight changing what it's doing right now. And that's what Ammar said. Ammar said, if you brake suddenly, do you stop with the car or do you move forward a little bit? That's why you wear a what? You wear a seatbelt, because the seatbelt is supposed to what? Decelerate your motion instead of what? Slamming into the what? Into the steering wheel. So inertia, every object with mass in this universe has what? Has a property called inertia. The only property that the only attribute that the object has to have is it has to have mass. It doesn't matter the size of the object, the dimensions, the color, the charge, the magnetism of it, doesn't matter. It just has to have some mass. So what's the only particle in the universe that doesn't have inertia? Light, because what's the actual particle name? Photon. Photon doesn't have mass, which means it does not have inertia. It interacts through a whole different other set of rules. Okay? The only attribute or feature of the object on which inertia depends is the object's mass. So now the question is, what's the relation between the mass of an object and the inertia? Do you think a massive object, like the bigger, not the bigger, the heavier the mass gets, the lower the inertia gets, or the bigger? Always bigger. If you have more mass, it's harder to both speed something up or slow it down, or even get it to move. Okay? What is inertia? It is defined as follows. Go ahead. So it is the what? It is the ability of the object to resist changes to its current state of either being in motion or at rest. Okay. Why is it important to talk about inertia when you talk about Newton's first law? Because most of you have heard Newton's first law, but not in the way I presented it to you in the first slide. You all probably heard it this way. An object at rest stays what? At rest, unless acted on by an external force to change its state. And an object in motion stays what? in motion with the same speed in the same direction unless it's acted on by a what? By an internal or external force. Always external force. You got it. That's why inertia is important. Inertia makes things keep doing what they're doing, whether it was nothing or something. Okay? So what are examples of inertia? Like, for example, Ammar said. So Ammar said, you're moving, you are attached to the car, but you're not a part of the seat. You're merely just what? Sitting on the seat. So if the whole car stops, the seat stops, right? But what happens to your body? Exactly. Your body wants to what? Keep moving. Okay? Okay. How about everyone? You're at a traffic light, everyone, eyes on me. You're at a traffic light, red, and then it turns green, and you floor it. What happens to your head? Is it really moving back? Your head is not moving back. When you slam the gas, what happens to the rest of your body? It moves what forward because it's pushed by the what? By the seat. What happens to your head? It did not move back. It just what? Stayed where it is. But relative to your body, what does it seem like? It moved back. Okay? Does it make sense? Obviously, you do feel the what? The tension in your what? In your neck muscle. That's why you get like a micro whiplash, effect. Okay? But yeah, it's not your head is moved back. No, the rest of your body moved what? Moved forward. So relative to your body, your head seemed to apparently have moved back. That's why they always say what? If you're driving very fast, you should have something where on the back dashboard of the car. Why? You're driving very fast and you slam the brakes and you have a pair of skates on the dashboard at the back. What's going to happen? The whole car is going to stop. But what about the skates if they're not fastened? What's going to happen to the skates? They're going to what? They're going to stay what? Stay moving. Yeah, that example you will never forget. Okay? So, in other words, a stationary object will fight, again, resist, fight, whatever you want to say, will fight to stay stationary, and an object in motion will fight to stay moving in the same direction with the same speed. Okay? In the same direction with the same speed. Okay, so let's go to the next slide. So, what is the general mathematical? Everyone, what did I call this? I call it a mathematical what? Yeah, I didn't call it a mathematical what? Or what? I did not call it a mathematical formula, or I didn't call it what's another word for formula? Starts with E. By the way, theory in technically, theory is like a body of what? A body of like sorry, theory is basically a statement or a body of statements that what? That means something. Do you see what I mean? So a theory could be an equation or could just be a what? A statement. Like the dual theory of what? Of particles. Particles are both a wave and matter. Do you see what I mean? So it could be a formula or an equation. Why do you think I didn't even call it a formula or equation? I called it a what? I called it a what? Come on, is that really an equation? I mean, technically it is, but does it have any variables or like a linear or a quadratic structure to it? No, this is merely just a what? A what? What did you state? F net is equal to what? There we go. So whenever you say F net is equal to 0, this is basically code for saying what? The object is either at rest or the object is moving at constant what? Why didn't I say a constant speed? I mean, I did use this speed in the slide before and the slide before that. Why did I opt now to say velocity? I'll give you a hint because it makes things easier to say. Ahmed. Because velocity is a vector. And when you say a constant vector, that means how many things are constant? Two, magnitude and direction. There you go. So whenever you say constant velocity, you're telling me I'm at constant speed at constant direction. You don't have to tell me both because a vector is made up of always two things. Perfect. Ladies and gentlemen, this equation is the building block of what kind of engineering? Why? Because you hope that civil engineers deal with what kind of structures? Moving or stationary? Stationary as much as what? As much as possible. So you want to piss off a civil engineer? Just tell them, really? I could have just taught you this in 2 minutes instead of 4 years of doing civil engineering. Civil engineering is built, by the way, just so you know, civil engineering is built on two equations, really. This and another one. We used to do it in grade 12, not anymore. There's an equation that looks like this. Again, don't copy it. Does anyone know what letter is this? It's not a T. It's a Greek T. Does anyone know what's the name of Greek T? Come on. No? Hey, no, say there's this. The one name. T. Has anyone heard of the letter tau? Tau. This, how many people heard of this word? What's this word? Can someone read it? Torque. What is torque? When something gets torqued, or when you apply torque to something, what does that mean? Say again? Not quite. Rotational. When you torque something, everyone, right now, what am I doing to the door? Am I pushing it linearly or circularly? That's applying what? Torque. Civil engineers base their entire structure on two principles. They hope that the building does not what? Stays at what? So it doesn't move linearly, but it also doesn't what? Doesn't twist. Do you see what I mean? So they basically build such that F net is equal to 0. And what was the name of this again? Tau net is equal to what? Which means there's no torque on the building, and there's also what? No what? No force, no linear force on the building. Obviously, does any building really stay 100% stationary? No. I mean, what happens to skyscrapers as they get taller and taller and taller? Does it get easier to build or more dangerous to build? Harder to build. Why? Because basically, as you go along, the structural integrity of the building is slightly compromised, which means the wind effect could actually twist. That's why actually now, for the last 20, 30 years, they have buildings with material that could actually it could exactly flex or twist under what? Under shear, under wind. Why? Because you don't want the what? Because, okay, what's the difference between this and a brick? Can I bend a ruler? So does a ruler give in? Yeah. And once you remove the force, what happens to the ruler? It goes back to what? Its natural shape, right? How about a brick? Is this brick now under tension? Of course it is. It's being pressed by all of these. But a brick does not bend. A brick handles pressure until it just suddenly what? Snaps or cracks. So that's why they build material with a little bit of what? Flexibility in them. Okay? They actually have, Western has an amazing, how many people have heard of something called the wind tunnel? Wind tunnel. Western has one of the top wind tunnels in the world. They build a scale, they tested the World Trade Center. They actually tested Burj Khalifa in it as well. They build a perfect scale model of the building, and they basically just blow fumes to see how the streamlines are and how the currents of air actually circulate, and they actually can calculate the force on it and see if the building is going to be structurally with integrity where at the top levels. Yep. Western has one of the top civil engineering departments in all of Canada, if not in North America, actually, because of that wind tunnel. Okay? All right. So look at all of these problems. Just give them a look. If you're wondering, why are you showing us this stuff? Are we going to do these? No, we won't. But those are taken from first year engineering at Western in the course called statics. When something is static, what does that mean? Is it moving or not moving? Static. I'm static right now. Static versus dynamic. Dynamic means moving. Static means stationary. All of those problems are taken from first year statics course. All of those problems are based on what equation? F net equals 0. And also what? Tau net, torque net equals also what? Equals 0. I know they look horrendous to look at. Yeah, right now. Because you've never done 3D analysis of vectors before. Well, guess what? By the end of the calculus and vectors course, you will actually start looking at these and actually understanding, oh, okay, so there's a vector of tension. There's like a force here pointing this way, and there's a force here, and there's a force here. and also what there's a force here holding this whole thing together. Same thing here. This there's a basically like a there's a pin here that makes sure that this one does not slide, this one does not slide, doesn't slide, doesn't slide. So this stays the same. Same thing with this pipe. Same thing with this, what we call a variable load. Trust me, this seems insanely tough now. After first year engineering, we're like, wow, I was actually able to do most of these. Okay. Obviously, we won't do 3D stuff in grade 12, but this will actually be relevant to anyone who does engineering next year. Okay. All right. Let's watch this video. So, all right. All three videos we're going to watch today are from the same channel, NASA Johnson.
Hi, I'm Sunny Williams, and I'm an astronaut who's lived and worked aboard the International Space Station, an amazing research laboratory that's orbiting the Earth about 250 miles above us. While we're at the space station, we astronauts live and work in a microgravity environment. Do you think the laws of physics will hold up in the space station while experiencing microgravity? Let's check with NASA astronaut Mark Van de Hei on the International Space Station to find out.
Newton's first law of motion says an object at rest tends to stay at rest unless acted.
You see what's going on here? All he did was what? Was just left it, and he just did what? He just removed his hand. But he removed his hand in a way to make sure that he doesn't what? He doesn't drag or what? Or basically what? Like spin it or torque it. Exactly. So when he left it, is there any force acting on it? Right, by the way, right now, what are the forces acting on the ball right now? Is there any, technically, is there any gravity by the Earth on it? No, it's very far. Is there a gravity on it by the space station? Yes, there is. But as we calculated from the gravity between, for example, you and you, gravity between objects that are not plant-sized are big or small? Small. That's why the gravity on it is very, 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 very small. Okay, is there any tension on it? Friction. Applied. Normal. So would there be any reason for this to move? Nope. You set it at rest, it will stay at rest forever unless he acts on it by another force.
Acted on by an outside force. Also, an object in motion tends to stay in motion unless acted on by an outside force, like my finger.
Okay, watch what happens.
Newton's first law of motion, so an object in motion.
Did you see that? Did you see that little push he gave? Okay. What do you think is going to happen to this ball if he does not actually stop it with his finger? Is it going to move forever? Yes, it will move forever. That's why astronauts, when they're doing any external repairs or spacewalks, they're always what? They're always tethered. They're always what? Connected. Why? Why do they have to be connected to the space station? Because what could happen if something pushes them like this? So let's say, for example, Josh is an astronaut in deep space. I'm a very small comet. He's good. He's working on something, but he's not tethered. And then even a very small comet pushes. Okay, what's your speed right now? No, what's your speed right now? 0. So you're at rest. Now there's contact between me and him. As I'm in contact with him, what am I doing to him? I'm accelerating his motion. And then I go away. What's going to happen to you? Are you just going to come to a stop or go and move on forever? Okay, so his speed initially was what? 0. And then I started speeding him up to 1 meter per second, 2, 3, 4, whatever. Let's say that I let my hand lose contact when you build up to a speed of what? 4 meters per second. Guess what? If Josh is not tethered, Josh will wander through space in a perfect straight line, absolutely no deviations, forever. At what speed? 4 meters. Just like this little ball will do.
Tends to stay in motion unless acted on by an outside force.
It's amazing. See how serene and quaint the movement is. It's perfect uniform motion. No change in direction, no change in speed. Absolutely nothing. By the way, is it still spinning? Yeah, it was spinning. Why? Because when he pushed it, he
stay in motion unless acted out.
did he push perfectly on the center of mass, or did his fingers spin it a little bit? Guess what? It will also keep what? Spinning. Also what? Forever, never, ever stopping. Okay? That's the key to what Newton's first law. Newton's first law says once you act on it with a force, if nothing is there to stop this force, that object will go forever. What are the possibilities that this ball could come to a stop or change its direction? How can you stop this ball? You can actually physically what? Just stop it. Or exactly, if it's in deep space, you, for example, an astronaut, if you ever wander into what? Into the gravitational field of a what? Of a moon, you yourself will become what? Will become a satellite. You see what? Because then you will be actually what? You'll start experiencing what? Gravitation towards that center, and you will actually spiral inward. Okay?
Down by an outside force, like my finger.
Let's look at this from another angle. Over time, the International
All right.
Space Station.
Perfect. All right. So always remember the principle I just did with Josh. I push. He builds up speed. He has no control. He's not tethered. That means he's going to go on forever. Okay. Newton's what? Second law. Now, can someone remind us again what two cases, only two cases, Newton's first law worked for? Only two. Either perfectly at rest or constant speed like that ball just going through. Now, let's be honest. Is every object in the universe either at rest or cruise controlling? No, most of the time you're either what? Speeding up or you're what? You're turning and changing direction. Well, guess what? All of these cases, Newton's first law fails for. So what did Newton have to invent? A what? A second law. Okay, so what's the statement of Newton's second law? What was the statement of Newton's first law? F net had to equal what? So what's the opposite of equaling 0? Not equaling 0. Yes, as simple as that is. You're right. So if the net force now is not 0, if the net force now is not 0, the object now can exist in not just two states, in actually three. Can someone guess what those three are? I just acted them out to you right now. Speeding up or accelerating, slowing down or decelerating, or change your direction, even if you maintain the same what? The same speed, like when you take a roundabout, for example, and you drive and you set the speedometer on the same value and you just keep turning. That technically is Newton's second law. Because first law is very strict about what? Maintaining the same what? Same direction. Yes. So the object could speed up, which means accelerate, slow down, which means decelerate, or change direction. I don't care. You can call it turning, curving, whatever. Okay. So basically, this means if you combine the forces, by the way, you're always combining forces. That's the whole idea of net force. That's why you had to study it first. If you're combining all the external forces in an object, and somehow you find out that the overall combination did not give you a perfect 0, you know two things. Number one, the forces did not cancel out. Why did they not cancel out? Who knows? Most likely they're not perfectly lined up, or the force magnitudes did not perfectly cancel each other when you added them as vectors like we did yesterday. For whatever reason, they did not cancel each other out. Some little net still came out. Okay, you know that the object is either speeding up, slowing down, or changing direction. It doesn't have to be turning. I just like to use turn for any change of direction. By the way, even if the turn is very small, like this, for example, like even if the turn is very, very unnoticeable, like this, for example, like even if it's a very, doesn't matter. Even if it's like a small curvature, as they say, technically, it is Newton's second law. Okay? What was the mathematical statement of Newton's second law? Sorry, first law. F net equals what? Yeah, it was not worthy of being called an equation. It was a mathematical statement. You stated that your net force is equal to 0. Okay? However, so can someone tell me what's the mathematical statement of Newton's second law? F net doesn't equal to 0. You just cross the equal sign. All right? There we go. So if you ever know that an object is accelerating or decelerating or turning, you know that somehow all the forces on it did not perfectly cancel out. And vice versa. If you know that the F net is not 0, you know that your object is in one of these 3 cases. Obviously, it could never be in more than 2 cases at once because it doesn't make sense to accelerate and decelerate at the same time. Okay? Yes, absolutely, 100%. Yes. But yeah, but that usually it's just called what we just cover it under turning, okay? And then we analyze what if it's speeding up while turning or slowing down while turning. So there's a problem with this statement. This doesn't really tell us much about the system. This just tells us one thing. Sorry, 1 second. This only tells us that just says that since the forces do not cancel out, the object has no constant linear motion. Well, physics can't be this ambiguous. I mean, physics is always the subject where you have equations that are so precise and accurate. They calculate like so many things with very good precision. So this can't be all we can do. This can't F net is not equal to 0 really has no variables or anything to it. So there's got to be another equation. There has to be another equation that is the building block of what? Of Newton's second law. Of Newton's second law. All right? Well, ladies and gentlemen, here it is. Give you 30 seconds to finish copying this. Okay? Oh, all right. Okay, let's watch this video now. Actually, let me go to the next slide and then show you. Newton's one of his biggest achievements. Newton is remembered for 3 things. Number 1, inventing calculus with another German gentleman, Gottfried Leibniz in Germany. Okay, but Newton did it from a physicist point of view. Leibniz did it from a mathematician point of view. So that's the first thing he did. The second thing is he discovered the concept of gravity. Third thing, this equation. This is the most important equation in grade 12, as long as forces are concerned, and in first year physics, and in most of engineering as well. F net equals ma. This right here is like our E equals mc squared. Everyone knows A equals mc squared. Well, guess what? This now is our E equals mc squared. I'm saying that this is now even more important to us because E equals mc squared is only for advanced physics. By the way, how many people saw E equals mc squared before? Does anyone know what it means? Real quick, in less than 1 minute. Energy for E, what's m? Always. And what's small c in physics all the time? Speed of light, exactly. And by the way, technically, whenever you have to say c, you have to say speed of light in what? In vacuum. You see? Because speed of light slows down if it goes like through your eye, through glass, through my lenses. It all slows down. So c is always what? Speed of light in vacuum. Any other speed always goes down. Slightly, but it still goes down. All right? Okay. So, question for you, everyone. Pencils down. What if the acceleration is 0? Does anyone know what happens after? Raise your hand. What if the acceleration is 0? Regardless of what the mass is, big, small, the mass is non-zero. So this is not a photon. Raise your hand if you would like to comment. What would this equation boil down to if your acceleration is 0, Ammar? Exactly. If your acceleration is 0, then no matter what the mass is, what's 0 times anything? So that means what? F net becomes what then? We get back which law? So what does that tell you? Which one is a special case of which one? Is the second law a special case of the first law? Or is the first law a special case of the second one? No. Other way. Think about it. You start with the second law, which is general, and then you choose a special case of what? 0 for A. You create the what? The first law. Oh, perfect question. Just so you know, historically, Newton did not propose these laws in this order. He actually proposed the what? The third law first. And yeah, from it, by the way, does anyone know what's Newton's third law? It's probably the most famous of all three. I'll start it off, and I know all of you can finish it. Every action has a what? Equal reaction. Equal in what? No, equal in magnitude and opposite in. He actually started by that, and from that, he devised the what? The what? The first law and the second law. But it's always been the physics teaching that you start by teaching what? You don't teach the laws, you teach the cases to which the laws apply. Do you see what I mean? So you teach the cases of at rest and what was the other one? Cruise control, or like constant direction, constant speed. And then you choose you teach what? The three other cases, which are what? What are the three other cases for this? Accelerate, decelerate, or change direction. And the third law basically brings everything together. Okay? So by special case, I mean what? You start with this. If your A is not 0, you're stuck with this, right? You just multiply mass times acceleration. But if your A is 0, the whole right side just becomes what? Which means you just created your what? Your first law. So your first law is the special case of 0 acceleration from the second law. That's what I mean. Okay? All right, so let's go back and watch that video.
Hello, everyone. I'm astronaut Randy Briskin, living and working for the International Space Station. Now, on the space station, we live in a microgravity island. You think the laws of physics will hold up? Come on, go find out.
Just so you know, everyone, just so you know, every astronaut, 99% of the case, engineers. Seriously. By the way, almost every astronaut has a Wikipedia page. Even if it's a small, description of them, they have a Wikipedia page. Look at every single degree they did. Almost 99% of them are what? Are engineers, and many of them used to be what? Test pilots for the Air Force. That's why so many of them actually are the ones flying the space shuttles. Many of them are physicists or computer science, but most of them are engineers or what? Or physicists. And in engineering, most of them are either electrical, mechanical, but obviously most of them are aerospace engineers. So when they talk about physics, they both studied it, built it as a lab, and then they experienced it in the best environment possible, theoretical deep space. No drag, nothing to really mask or hide the real effect of physics.
The acceleration of an object depends on the net force
Newton.
acting on the object, and the mass of the object, or F equals ma. Now we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate. I always thought it was something small, something I had at home. Oh,
Okay, so what does he have in his hand? Chapstick. Heavy or light? What is this? A rope. What do you think it's gonna do? Slingshot, yes. Stretch, give it some, we call it extension or elastic energy, and then what? Then what? Let go or release. Okay.
we'll go ahead and use our force in our punch report here. Click on our button. We'll pull it back. And you see how fast.
You almost didn't see it what cross the screen, right? Because it went so what? Fast. Okay, now here's my question to you. Okay, so at the beginning he was what? He was holding it. So what was the initial speed? Come on, eyes on me. The initial speed was 0. And then he lets go. What happens to the string? Does it go into more tension or less tension now? Less, because it was already under as much tension as possible, depending on how much you actually pulled it back, and then you let go. So now the tension is being stored or released? Released. Okay. So what's happening to the chapstick? As long as it's touching the string, it's accelerating. And then it leaves the string. Just like Josh was accelerating under my force until he left, until then there was no contact between my hand and him. Once the chapstick leaves the rope or the string, does it keep speeding up, start slowing down, or does it go on forever at the same speed? Again, at the beginning, it was Newton's what? Second law, because it was accelerating. And then once it left the force, it went back to what? Newton's what? Because it went what? Forever at the exact same speed. Okay? Perfect. All right.
You can see how
Less than a
fast
second. It
the
clears the screen.
acceleration is.
Okay.
Next, we'll try.
Okay, before he does it, what do you think is going to happen to this if he still stretches the what? If he still stretches the string by the same amount, which means still applies the same force to this. Does this seem to be lighter or heavier? Okay, everyone. What was the equation again for Newton's law? F net equals what? No, sorry, Newton's. You're right. Newton's second law. Second law. M times A. Okay. Is he subjecting both the chapstick and this little lunar module model to the same force? Good, because, well, we're hoping. Otherwise, you can't make an experiment, right? An experiment has to be fair. Everything has to be subject to the same conditions. So he should what? He should go and stretch it exactly to the same amount. Okay, so that means what? Is this going to change or stay the same? Okay. What happens to the mass between the chapstick and the lunar module, this model? Does it go down or go up? So this thing went up. But if you're trying to multiply m and a to the same number, F net, what should happen to the acceleration once this one leaves the rope or the string? Should it still speed up faster, same acceleration, or now go into a slower acceleration? Because then, if you multiply something that went up by something that went down, could you still potentially generate the same number? Yes. Like when I tell you, give me two numbers that multiply to 100. Go. Two numbers that multiply to 100. Any two numbers you want. Say again. 50 and 2. Good. 50 and 2. Josh, give me two other numbers. Still multiply to 100. Give me any other two numbers. 25 times. What happens to 2 and 4? It went what? Sorry, it went up, which means this one has to what? Exactly. That's the whole idea. If you're trying to produce the same product or same number, you have got to play a balancing game. So
Spaceship. We will mass it. You can feel that because as you move it, you can feel it. The kind of force, the extra force you push with your hand. Our spaceship on our launcher here. Stands by.
took longer or shorter time? Longer time, which means because it wasn't moving as fast. Okay, look what is good.
Same amount of force. Smaller, less massive object. These accelerations faster. This is the biggest and most massive thing we have. Let's see how the acceleration is
Mattress or something. Okay. Again, he has to.
Same amount.
Yes.
Force. Here we go.
Very big mass, very small what? Yeah, not speed, acceleration. But it also builds up to what? A smaller speed by the time it what? It clears the string.
Now I'm going to send it back to Earth.
Perfect. Nice. Okay, let's just talk about one more. Let's save Newton's third law for tomorrow. But let's just talk about one. Okay, so this was the rule or the law. Okay, so everyone, you don't have to copy this. Okay, just let's read this together. So what exactly does F net equals ma mean? Okay, it simply means that if you want to know the net force on an object, acting on an object from outside, you could either do one of two things. One of them we did yesterday. What did we do yesterday in the two worksheets? What did we do to a bunch of forces? We added them up as scalars or as vectors? Nope. Okay, you know what? You're not totally incorrect. Technically, when I added just the what? The scalars. But effectively, they were still what? Plus and minus, which means what? They still had what? Direction built into them. Make sense? Okay, so they might look like scalars, but deep down, they are vectors. So one thing you could do, you could add up all the forces affecting the object from the outside and see what is the overall force vector. If it's 0, it's Newton's first law. If it's not 0, it's Newton's second law. This is okay, but what's the bad feature about this? You could take a what? Yeah, why? I could give you 10 forces, and they could be pointing every which angle possible, which means it's got to take a long time to break them down, and you might make a mistake, okay? But technically, it's a very mechanical work. The other way is to what? Is to just multiply what? M times A. So that means you're going to need to know what about the object. It's what, and it's what? It's mass in kilograms, and it's what? Acceleration. So you can just observe the object for a little while, see how it accelerates or decelerates, whoever or whatever happens, and then multiply that by the mass of the object. This seems to be easier, but there's one word here that should, be a little bit of concern. You need to what? Observe. Acceleration is observing. You need to see and measure VI and VF and delta T. You basically have to pull some kinematics into the situation. So the bad feature here is that you have to spend some time watching the object's motion and hoping that you're really measuring things as accurately as possible. Okay? All right. So now we define the what? The Newton. What is the definition of a Newton? Well, did we use Newtons before? Yes, we did. When we calculated what? Force. The unit of the force of gravity or gravitation. Either way. The Newton is the standard unit for what? For force measurement, which is very fitting because Newton was the one who came up with the law. Okay? So the Newton is the amount of force that what? By the way, get used to this way of defining what? Defining units from now on. Everyone, again, get used to understanding how units are defined in grade 12 and first year. Any unit that has a person's name can always be defined this way. The Newton is the amount of force that is needed to do what? To do two things. To give an object of exactly how much mass? 1 kilo, perfectly 1 kilogram. An acceleration or a deceleration of how much? How much? 1 meter per second squared. Where did that come from? From this equation. Everyone, raise your hand if you see the relation between that equation and that equation at the bottom. And explain to me what happened. Explain to me what's the difference or what's the similarity even between that equation and the boxed equation. Go ahead. Can you tell me how I came up with that equation from the top one? Just raise your hand. What did I just do? By the way, this presents a very good trick for you to understand for future calculations. Ammar, everyone, listen to Ammar. Go ahead. Tell me your idea of what happened. Thank you. I subbed in. Force is measured in what? Mass is measured in what? Acceleration is measured in what? And then what three magic numbers did I use? 1, 1, 1. By the way, did I have to use 1, 1, 1? Okay, let me ask you a question. If I wanted to keep this one, but change those two, give me two numbers that multiply up to 1. Give me two numbers that multiply up to 1, but they are not 1 themselves. Just raise your hand. Say it. Half and 2. 2 times half is what? Is that the only choice we have? How many choices do we have? Go ahead, give me another one. 1/4 times what? Give me, no, times 4. Give me another one. 1/10 times 10. Now, so technically, can you tell me, everyone, raise your hand if you think the following way to define a Newton is correct. The Newton is the amount of force that is needed to give an object of mass of 10 kilograms and acceleration of 0.1 meters per second squared. Is that technically correct? But what's the problem with defining things that way? Do we have one definition or an infinite number of definitions? So what is the easiest triplet of numbers that we can use? 1, 1, 1. Get used to that. We're always going to be defining things this way. You look at the equation, you replace it with units, and boom, you just write a verbal statement. Okay? There we go. Okay? Go ahead, everyone. Write that down. Yes, that statement and that statement are exactly the same. This is just the mathematical way of saying it. This is the word way of saying it. Yes. So remember, technically, you can, as long as your mass goes up, your acceleration has to what? And if your mass goes down, your acceleration has to go up. Remember that space demonstration right there. Perfect. Okay, so what is the statement of Newton's third law? It's probably the most famous of the three. Every action has a what? Has a reaction that has two properties. What? Equal in magnitude, but perfectly opposite in direction. So that also gives you the vector nature of forces as well. Okay, so for every force in this universe applied by somebody on another body, there is a reaction force that is opposite in direction and equal in magnitude. Or you could say the other way, equal in magnitude and opposite in direction. Doesn't matter, those two conditions have to exist. Okay? So for every force, there's a reaction force that is opposite in direction and equal in magnitude. Okay? So basically, what does this mean? Okay? Again, I'm going to show you videos and animations to actually explain what that is. So, first of all, the most important thing for third law is that you always need how many distinct objects? Two, because one of them has to be pushing or pulling, neutral word acting on the other. So whenever there are two distinct objects in contact, they have to be in contact. With one of them, call it object A, physically pushing on the other, call it object B, it is indeed as well valid that object B is what? Acting, reacting. So object B is reacting by pushing back on object A with the what? With the exact same force. In what though? In magnitude, but it's what? Opposite direction. No more, no less. Okay? So that's basically one way to explain what, or to state, I should say, state Newton's third law. Okay, so let me just go now. Okay, to really understand this law, let's discuss what we call, Einstein popularized this term, thought experiment. Thought, how many people have heard of something called thought experiment before? Okay, where did you hear it before? Thought experiment. Or what kind of teacher mentioned it before to you? Have we been doing thought experiments so far? Yeah, almost every single day, right? Like when we go to theoretically deep space, that's called a thought experiment. Why did Einstein actually popularize this term? Because the only way 100 and about, like, let's say 100 years ago, that you could only discuss relativity was only through a thought experiment, because the technology was not there yet to actually do an actual experiment. Okay? All right, so let's just, pencils down. Let's just discuss this. Okay, so what do we have here? First of all, where are we? Here, deep space, which means what exists there? Nothing. No forces, no drag, no friction, nothing. So what you see is what you get, right? Perfect, 100% honest, portrayal and depiction of any force that happens. How many objects do you have? Two. What are they? A car and a basketball. Okay, fine. So what we're going to do is this. Okay. Let's discuss let's discuss any scenario that could actually result from this. So, scenario number one. The ball starts moving to the left, and the car keeps moving to the left with the same speed, with faster speed. How many people think that's correct? The ball starts moving to the left, and the car not only keeps moving to the left, but it speeds up. How many people think that is true or correct or logical or could happen? Come on, people. Thought experiment. Work those brain cells. How many people say that's incorrect? Okay, you know my style. You say it, you have to justify it. Who would like to justify why it is incorrect? Okay, Ammar. Why does that not make sense?
The car can't speed up because there's no forces being applied to it and can't use its engine, so it has to have friction for it to move forward, propel itself. Right now, the wheels are just turning, but they're in deep space. That doesn't do anything for the car.
Okay, here's another way to ask the question. Does everyone remember the third unit in grade 11 physics? We did kinematics and then we did forces. What was after that? Work and energy. Work and energy. When something speeds up, what does that tell you about the energy of that object? Did it go down or go up? Does it make sense for once this one actually moves this way, for this one to speed up? It has to what? It has to slow down. So basically, I know I didn't teach you what energy conservation, but it's so known of a principle, especially how many people did energy conservation in chemistry? Same thing. Chemicals never gain or lose energy. Everything is contained within the system. Okay? So no way. Why? Violation of energy conservation. Where did that extra energy for faster speed come from? Go ahead, write that down. So that's the first violation. Sorry, that's the first explanation why that cannot happen. Okay?
We can't write that.
Oh, sorry?
Like it's black, so we can't write. It doesn't show.
Oh, I thought you printed it like as light gray. Okay, sorry. Write it. Sure. Okay. Yeah. So what's up? You know what? Yeah, like maybe under it, just point to it and say energy conservation violation. That's it. Just tell yourself a few words that explain to you why this cannot happen. My bad. I thought I made it light gray. Okay. Scenario number 2. What's number 2? That can't happen. Impossible. Number 2. The ball starts moving to the right, and the car also what bounces and goes to the right. Is that possible? So it is possible that both of them go to the right? Oh, both of them. That's the thing. Both of them suddenly go to the right. Can that ever happen? No way. At least one object has to move where? To the left. Because of the what? Because of the force applied by the what? By the car on the what? On the basketball. Okay? And by the way, how can you start with a system? How can you start with a system? Or how you can have a system that starts with at least one thing going what? Which way? Left, and have everything then go what? Right. Can't be. It's impossible. Okay? So that makes no sense. How could a purely left side motion suddenly turn into right side motion? Okay? So you can say, for example, impossible. Directions can't flip like that, especially all directions. Okay, so 2 scenarios now, impossible. Let's discuss the other 2. Can someone tell me one of the other 2 that could actually happen? Come on, raise your hand. There are only 2 things that could happen here. Okay, Ahmed give us. Okay, Umayma give us one.
They either like when the car slows down.
The car what?
Slows
down.
And the ball moves.
And the ball what? Okay, that's one way. What's another thing that could happen? Which is okay, technically it's possible, but it's highly improbable. Josh.
Highly improbable?
Oh, you think so?
Oh, then I don't know. The car passes right through the wall.
Sorry, the car what?
The car passes right through the wall.
Okay, but that means what? That means that the ball doesn't exist. Again, if an object exists, it has to what? Okay, what was inertia again? What's inertia? Because that relates to inertia. Every object fights to what? To keep doing what it's doing. This has mass, there's no way it's going to go through it. You might say shatter, but that means what? It still went through it, and other objects moved what? Moved in different directions. So let's say nothing shatters here. Yes, Ahmed.
Ball stops.
Sorry?
The ball stops.
So the ball stays stationary.
No, like 2 objects stops when they hit.
Is that possible? No. Energy conservation. Where did that energy go? It had to go into some motion, even if that motion is what? Is very very, very small. Okay, Allah?
The ball moves to the left and the car moves to the
So
right.
so one way is what? The ball moves, and what happens to the car? But that would be what kind of a ball? A very light or a very heavy ball? Yeah, because it was able to what? Bounce back a car. Okay, what's another situation that's also possible, but highly improbable? The ball, okay, what happens to you when you throw a ball at a wall? What happens to the ball? Goes back. What happens to the wall? So technically, what could happen to the ball? It could what? Stay still, and all the energy would be what? Bouncing the what? Bouncing the car. All of these scenarios are possible. Are they possible? But are they have the same probability or no? No, some of them are more probable than the other. So, scenario 3, the ball starts moving to the left, and the car bounces and starts moving to the right. All right, that's one way things could happen. This one super heavy basketball, again, not super big, super what? Because inertia does not depend on size, it depends only on what? Mass, just how much matter or substance is inside of an object, not how big it is. Okay, but physics says it is possible. By the way, we're gonna do things like this when we actually study the third unit. I'll tell you the name just in a few minutes. Okay, man. I mean, this is possible. All right. The ball starts moving to the left, and the car keeps moving to the left, but with what kind of speed? Higher or lower? Definitely lower. Why is that? Because when you lose energy to another object, what happens to your own energy? It went down. And when you have lower energy, can you go faster or slower? There you go. So, and the car keeps moving to the left, but with a slower speed. Yes, Josh.
Can't also the car like use all of its
Energy
energy
or force.
to push that ball and then it stays completely still?
Yes, that's another way. All of the energy what transfers to the what?
The ball.
To the ball, and the car what? Stays still. That's one possible scenario, right? But that means what? Okay, we're going to talk about collisions, or we're going to talk about perfect collisions and imperfect collision. The one you just mentioned is that's a what? That's a perfect collision because all of the energy purely 100% transferred to what? To the what? To the second stationary object. You're right, 100%. Technically, all of those are possible, but with higher probability for some of them. Awesome. This is the most likely thing that is going to happen. Thumbs up. Okay? All right. Okay, so let's go to the next slide. Okay, so since it will be most likely that scenario 4 is going to happen, two simultaneous means in sync events must happen. Number one, the ball is what? Is what? Shot. What does shot mean? It's started from what speed? 0, and it what happened to it? It what? It accelerated to the what? To the left. Then, what the other thing happened? The car must what? Technically be shot, but where? When you slow down, it's like you've been shot, but forward or backward? Exactly. When you slow down, you're being what? You're being yanked backwards. So the car must slow down. So, how many objects do we have here? Two distinct. Are they touching so far?
No.
Not yet. Okay. So what's going to happen when they touch? How is the car pushing on the ball? To the left or to the right? So the car is pushing on the ball that way. According to Newton's third law, how would the ball react to the car? Which way would it push?
Push to the right.
Exactly. And now does it make sense why the car what? When this pushes back on this, when you push back on an object that's already moving, do you speed it up or slow it down? And that's why it slows down. Because Newton's third law tells you that, okay, everyone, initially, what's the speed of the basketball? What's the speed of the basketball right now? 0. Can you ever get slower than 0 speed? Which means the only possible change of events is for that ball to start what? To start moving, which makes sense because suddenly it will experience a force going this way on it. The car now is going to respond to an acting or a reacting force, but is it with it or against it? Whenever you push against an object, do you speed it up or slow it down? Slow it down, and that's basically. So for a stationary ball to move to the left, the overall force must point to the left. So go ahead, write that down. Make an arrow somewhere in the ball's body and point to the left and say F, car on ball. Remember, everyone, now, whenever you do Newton's third law, you can't just say, listen to me carefully as you write. Whenever you do Newton's third law, you can't just say Fn, Fg, F applied. No. You have to mention how many objects. How many? Because there's one object pushing on a what? On another object. I am pushing on Ammar, which means this is my force on who? You see, you always have to mention how many? 2 in the subscript, just like a relative motion, V, A relative to B, and so on. How about the force pointing in the car, on the car? It would be a force of what on what? Do you see how I sketched the forces? Did I sketch them technically coming out of the exact same vertical line? Yes. Technically, they should be both pointing from the same point of what? From the same point of contact, technically. But what did we say about vectors? As long as you move vectors, but you don't change their what? Their direction or magnitude, you can place vectors any way you want on a what? On a 2D or a 3D grid. Remember about this, by the way, this is a very important and helpful principle in vectors. As long as you move vectors anywhere you want, but you keep what to each vector? It's what? Magnitude and direction. You can place the vectors any way you want because you can bring them back again to what? To be tail to tail. Just like when we did all of these vector addition decomposition stuff. Okay? Yes. All right? Good? So, here's a very interesting thing. Everyone, vessels down. The law says what? Every action has a what? Opposite direction, but what? Equal in magnitude. What does that mean? It's very counterintuitive, but that means, God forbid, someone gets hit by a car. What did they also do to the car? They pushed it back with the what? With the same amount of force. Do you see what I mean here? Mike Tyson hits you in the face. Guess what? Your face hits Mike Tyson in the fist back with the same amount of force. But who got more damage? Your face. Now my question to you is this. A car hits someone. Both of them are pushing against each other with the same what? With the same amount of force. Then how come the person flies away and the car it slows down but barely, just like this situation? What's the reason here? Raise your hand. Wallah. Because it's what? Remember inertia? Which one is easier to change the state of? The car or the basketball? Why? Because the basketball has smaller what? Smaller mass. Smaller mass means what? Smaller what? Inertia, which means what? Is it going to fight more or less to change? It's going to fight less, which means it's easier for this one to what? To what? To shoot this way, but it's harder for this one to what? Shoot this way. So what happens to this one? It just what? Slows down. What would happen, everyone? What would happen if the car and the ball have the same mass? Huh? What's the possibility? Right? Why? Because the same effect on this one should be the what? The same effect on this one. Remember yesterday when the astronaut did the slingshot? When he actually, retracted the string and what happened? Now, did he use the same object 3 times? Do you remember what was the first object he used? Chapstick, which is very what? Good. You said light, not what? Not small. Perfect. What was the next object he used? No. Like a little metal, like module, which was heavier than the what? Than the chopstick. What happened to it as it moved? Did it spring as fast or slower? Because it has a bigger what? Bigger mass, bigger inertia, which means the force effect on it is what? How about the big mattress, I think, that they pushed after? What happened to it? When the force pushed it, it was moving very slowly because the mass is what? So it did not want to speed up as much as the first 2 objects. Is it making sense now? So I know it's so counterintuitive. How could I push back on the grill of a car hitting me with the same amount of force? Oh, you were pushing. But because you have a smaller mass, you experience more what? More what? More. Change in speed is called what? Acceleration. Why do you think Newton's second law is more relevant than Newton's what? First law? Because mostly things what? When they actually have a force on them, what happens to them? They accelerate or decelerate or turn or switch direction. Exactly. All right. Okay. Let's watch this video right here. It's already queued up.
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an
Actually, in microgravity, it holds up perfectly, right? Because because there's nothing else masking its own effect.
Equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business.
Did you see how he just moved which way? Why? Because he was pushing the what? He wasn't pushing. He was not. Technically there's no ground here. He was pushing the what down? The ball. That ball still what? Push it. Would that ever happen on Earth? Because what? Because gravity what? Dominates everything.
We've got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied.
It's tricky because do we barely see him move? Do we see him move? Yeah. Did you? I didn't. It was so what? So small. I didn't see it, but we know he what? We know he moved forward or backward. What would have been a better way to actually do this experiment? For him to do it, or for another astronaut to throw a ball at him? Okay. Amar, throw this at me. Go ahead. Go ahead. Not to my ears. Work on your aim, my friend. All right, everyone. Okay. Did I move? No, I didn't. Why? Because there's what? There's friction. What if he did that to me in space? Would I actually move? Of course I would. Even with what? A very small what? But we know that this, once it hit me, it's going to bounce back slowly or fast. This one. This one will bounce fast, right? I will bounce just what? But would I still move? I would, because that energy is now between me and the what? And the eraser. Does it make sense? But on Earth, you can't see that. Why? Because of what? Because of friction. By the way, even if I am hanging from the ceiling and there is no friction, can you still do it? No, because what is still pulling me down? Gravity. Gravity masks everything. That's why we need to go theoretical vague space. Yes.
Can you just tell a person?
Say again?
Like if you
Oh, did you see that video before? Because that's exactly what he's got to do right now.
Oh.
Yep. Look, everyone.
See, the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something.
I know they're astronauts and geniuses, but Joe seems a bit too terrified for this experiment. Like he's going like, hello.
Can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him.
He pushed, he got pushed. Right? With the exact same amount.
Notice that when I applied a force to Joe,
the only way they would both bounce with the same acceleration is if they both have the exact same what? Mass. But depending on who is what, if someone is heavier, they bounce back what? Faster or slower? Slower. Why? Because mass goes up, acceleration goes down. It's both a ramification or a consequence of Newton's second law, F net equals ma, or Newton's third law. Same thing.
Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space.
Okay, so now you don't have this animation, I think. You have the car, I guess. Yes, you have the car. Okay, so what you have is. Oh, okay, sorry. So go ahead and let's do this this slide. So this is the what? This is how technically this is the equation of Newton's third law. It is so simple, you're like, really? That's it? You're just telling me that FA on B is the negative of FB on A? Yeah, it's negative interaction equal in magnitude. Remember, you always need two objects. And I always like to follow this. By the way, I don't treat this like relative motion. Relative motion, we used to say VA, BAC, BC. No, here, I actually explicitly say A on B, B on A. That's why Newton's third law is called the force pair law. Force pair, because you always need what? You always need a pair of objects, which means you'll always be doing a pair of forces. So by the way, if we think of Newton's third law, what does this mean according to this situation? Everyone? What did I just do? Jumped. But then I what? I landed. When I landed, which way did I push the entire planet? Down. I pushed the planet down. And the planet pushed me what? Pushed me up. Which one of us, though, experienced a bigger change in speed? Me or the planet? Why? Okay. When I came to I decelerated very slowly or very quickly? Very quickly, because I have a small what? A small mass. But the Earth actually what? Accelerated which way? Down, but with a very what? Big or small amount? Because it has a huge mass. Remember, mass and acceleration are basically what? A balancing act. Always a balancing act. What's going to happen here? Obviously, those two things are going away or into each other. Into each other. So, which one? But okay, first of all, right at this contact surface, right at this contact right here. Right at this contact. Are the forces equal? Yeah. No. Are the forces always equal? Yes. Newton's third law, the truck pushes on the golf cart exactly with the same amount of force that the golf cart pushes on the truck. So can someone tell me how to put the force directions on this? Laser pointer to whoever wants it. What's that question? Good, yeah. Listen up.
Are they like going into each other?
Yeah, at that moment they touched and they collided head on.
Yeah, but like, what if they're going at different velocities?
Again, doesn't matter. See, everyone, listen. What does Newton's third law say? Is it the velocities that matters or the forces? The forces, and from the forces we're going to get what? The backward acceleration from them. See, it's not yeah, you know what? Why are you even asking me about velocities when I already showed you a basketball that didn't have any velocity being hit with a what? Car that had all the velocity? You see what I mean? Velocities don't matter. What matters is the force and acceleration after. Okay? Good. That's why Newton's second law is what? F net equals what? F net equals what? What's Newton's second law? F net equals m times a. Not what? Not v, not distance, not time. Do you see what I mean? That's why the only thing you can show in an FBD is what? Acceleration. Remember? It tied into what Newton's second law. Who would like to answer me this question? Which way? Okay? Omar, hold. Which one do you want to give me first?
So the truck.
The truck?
From this line.
Yes, sure.
The force on a car on a truck would go that way.
Okay, so everyone go ahead. So force. Again, technically everything should be at the contact point, but it just gotta be way too busy here, so I'm just gonna say the direction. So this would be
Force of car on truck.
Oh, actually, do you think we can put that force here, everyone? Like here on the truck itself?
I mean, but,
Yep.
Yeah.
Yeah, because technically that force is acting on the truck by the what? By the cart. So go ahead. By the way, you can do it here, you can do it here, up to you. But here it might look like friction. So here it would be what? F. This would be the what on what?
The car.
The cart on the truck. So cart on truck. Okay, how about this way?
Right here, the force of
Yep.
car on the truck.
You got it, everyone. F, truck on cart. Awesome.